Okay, we've reached the heart of it. So what's so cool and powerful about vectors is you can describe simple motions by transforming vectors. So you know how to do a circular motion and you know how to scale a vector to create a linear motion. Because vector addition, you can think about graphically as follow one path, and then a different one. You can break a complicated motion down into individual simple parts that you add together. And that's why vectors are powerful. Well, one of the many reasons. It's because it makes it very easy to describe complicated things by breaking them into simple parts. So let's take our first couple of steps in that direction. Let's pretend we wanted to describe this red point as it moves around a circle centered at 5, 10. So you can think about this as the sum of two vectors. We've got a vector that takes us from the origin to the center of the circle, and then we have another vector which takes us from the center of the circle to the point on the outside as it's spinning around. Okay, so why is this helpful? So if I want to imagine this vector that just rotates here, remember that vectors don't live anywhere particular on the plane. So this vector is really just saying go over and up. Or, later on, if it's rotated to be over here, it's saying go over here and up. So what describes this red vector? The red vector, which we'll call v, is just the one that you're familiar with. It's cosine t sine t. And again, it doesn't matter that it's at 5, 10 because this vector v is just describing the displacement from the tail to the head. And so if the vector is a length of 1 and it's spinning around in a circle, it doesn't matter if the circle is located here or there or wherever. It's always going to be that same vector. So if I want to describe the position of my point moving around in a circle, I can always find that point at any time at all by first following the position vector to the center, and then following the velocity vector from the center to wherever the point on the perimeter is, because the velocity vector is just spinning around in a circle. Okay, so that wasn't actually combining motions, right? We just had a vector that wasn't moving followed by a vector that was spinning around. So let's make this one step more interesting. What if the point is rotating around the circle, but the circle is also moving slowly to the right at the same time? So that's a little bit hard to think about. It might make a kind of a spirally shape like this. Hard to say. But it's very easy to describe with vectors. Let me show you. Let's start by forgetting that there's any rotation at all. Let's just describe the center of the circle as it moves with time. So this is like the stuff that you were doing last week. You could have a position vector that takes you to the starting place at time equals 0. And then we have to describe the velocity vector for the center of the circle as the center is moving that way. So let's pretend at time 0 it's here, and at time 1 it has moved, let's see, 1, 2, 3. As usual, my drawings are terrible. Let's assume it's moved from 5 to 8. So it's moved 3 to the right. So if I want to write an equation for the vector that is the position vector for the center of my circle, I know the center of my circle. I can always find it by starting with its initial position and then adding time times its velocity vector. And here it looks like it's just moving straight to the right, and it's moving by a distance of 3. So time times 3, 0. All right, so now imagine as time's going up, this whole circle is kind of slowly moving in that direction. So how can I describe the position of this point? I'll start by following this vector and that vector to take me to the center of the circle, wherever it is as it's moving. And then I'll follow the red vector, which is just spinning in a circle, and we're imagining that it's always centered on the moving circle. So the red vector equation is just the same. This is still cosine t sine t. So if I want to know where the red dot is, I'll just add all 3 of those vectors together, which I've written here. So position, how is the center moving, and then plus the vector that takes us to the rotating point. So this is the position, This is the velocity for the center of the circle, and then this is the rotating vector that I follow as the last step to get to the end. If you want to see these on Desmos, remember that these equations that we're writing are pretty much just like parametric equations. So if you think about the x component as being x as a function of time, and the y component as being y as a function of time, in Desmos, you can just make these two equations and then use what you already know about parametrics to imagine what does the end of that velocity vector look like over time. So if I'm going to combine all three of these together, I'll just combine all the x components and all the y components separately. So that will give me the red dot as a function of time is going to be 5, excuse me, and then t times 3, so 5 plus 3t plus cosine t. And that's the x part. Then the y part is going to be 10 plus t times 0, which I'll just leave out because it would be silly to write it, and then sine t. Cool. So then this is y of t. Let me just show you what it looks like in Desmos right now. So here I am. I'm going to write x1 as a function of time is 5 plus 3t plus cosine t. And then y as a function of time is 10 plus sine of t. And I don't want to display these separately. Instead, I want to display x1t, y1t. Time between 0 and 10 seems good. Interesting. So this is the path that it's tracing out. And it might not be apparent to you kind of why that's true. Let me add in a little bit of the rest of this so you can see it. Okay, so I've made a slider for time now, so you can see as time goes up. Here's the point, but it would be helpful to imagine, like, what does the circle look like? So here I made an equation for a circle that's going to move at 3 units a second to the right. So now it kind of makes sense. You can see the dot rotating around the circle at the same time that the circle's moving. So you can see that this was very difficult to visualize when it's just you and the piece of paper. But you can totally write equations that take the complicated motion and break it into 2 simple parts, a linear motion and a circular motion. If you wanted to, you could make the point rotate around the circle much faster. So all I did was replace t with 10t, but just for the vector for the rotation. The linear motion of the big circle is still the same. And so now you can see what it looks like. So you can see the circle's moving at the same speed, but the point is rotating much, much faster. Let's do it the other way. Let's say we're going to go back to a slow rotation, but we're going to have the circle move more quickly. So instead of 3t, let's make it 8t. So now it's looking a little bit more like a sine wave, although it is not. Oh, sorry, I didn't make this circle move at the same speed. Okay, there we go. So you can see the circle's moving much faster compared to the rate of rotation, and so you end up with a different overall path. Okay, so what if we have a circle that starts at 4, 0 and moves in the path of a circle along this direction, and then meanwhile we have a point that is rotating around the perimeter of this circle, so it's going to be sort of a up this way kind of thing. What is an equation, a vector equation, that would give us the position vector for the center of the circle as a function of time? Well, in this case, we can imagine this is time 0, and this vector is just rotating around this way. So it's like a big circular motion. So it makes sense that the vector would be cosine t sine t, except that this vector's overall length is 1, so that would actually be this circle here. So we have to scale the whole vector up by a factor of 4 to describe the larger circle. So we can multiply by 4 on the outside. Okay, now give me the equation just for this, the rotational motion of this red point around and around the center of this circle. And let's assume that we want this red dot to be rotating more quickly around its center than the purple dot is rotating around that center. All right, so it's also going to be cosine times sine, and in this case, this circle is radius 1, so we don't need the vector to be any longer, so we don't need to scale it. But we do want it to be rotating faster, so instead of putting t's, I'm going to put something like 10t. All right, last of all, go ahead and tell me what is the full vector equation that will give me the position vector of this point as it's rotating around up this way. So it's just going to be the vector that points to the center of the circle, and then after that, the vector that points from the center of the circle to wherever the point is. So if we're going to write it out fully, it would be 4 cosine t sine t plus cosine 10t plus sine 10t. And if we wanted to group all the terms together, the x's and y's, we could write, let's see, this is going to be 4 cosine t plus the x term over here is cosine 10t. And then for the y's, we've got 4 times sine t, and then plus sine 10t. And if you want to check out what that looks like in Desmos, go